Hi, and welcome to a new lesson from Easy Chemistry. This is Mr. Kusai, and today we're going to continue what we started last video. In the previous video, we were talking about the acid and bases. We talked about the electrolytes, and we talked about the uh, how we solve the pH for weak acid and also the pOH. We talked about the steps that are followed in order to solving weak acid ionization problems. We took this problem, which was in this problem, they were asking for how much the pH for a solution concentration was given, and as well as the Ka for this weak acid, nitrous acid. Today we're going to have another type of problems when you have the pH and when you have the concentration, and in the problem they are asking you for the Ka, how it's going to be solved. The pH of 0.1 molar solution of formic acid, which is weak acid, is 2.39. What is the Ka for this acid? All right, so always the first step we need to follow is to write the dissociation equation for the weak acid, which is HCOOH yields to double arrow because it's a weak acid. It doesn't dissociate 100% to give you H positive plus HCOO negative. And we need to follow the ICE table. I is the initial concentration. For this weak acid, it was 0.1. And for the hydrogen, initially it was 0 because there is no hydrogen ions in the solution, as well as for the formate ion, it's going to be also 0. The change, because the formic acid was being consumed, dissolved or dissociate, so it's going to be negative X, and for the H positive is going to be positive X, and for the formate ion is going to be also positive X. Now in the equilibrium or at the equilibrium, we need to add the initial and the change is going to be 0.1 minus X, 0 plus X, and 0 plus X. Now, here they need the Ka, and we have the pH. From the pH, as you know, we can calculate the H positive ion, the concentration. So pH equals to negative log the concentration of H positive. And that means we can find the H positive by taking the antilog of the pH, which equals to 10 to the power of negative pH. And in this case, it equals to 10 to the power of negative 2.39, which equals to 4.01, 4.07 times 10 to the power of negative 3 molar. Now we have X already. And from this, we can find Kc, it equals to the concentration of the product divided by the concentration of the reactant. It means that it equals to concentration of H positive multiplied by concentration of HCOO negative. Don't forget, at equilibrium divided by the concentration of HCOOH. All of them at equilibrium. So it's going to equal to X squared at equilibrium, X multiplied by X divided by 0.1 minus X. And as I told you, for now, we're going to neglect this X. We're not going to involve it in this reaction or in this equation. Later on, we will learn when do we neglect it and when do we need to solve a quadratic equation. All right, so now we have the concentration of H positive, which equals to X. We need to compensate this X here in this equation. So Kc is equal to 4.07 times 10 to the power of negative 3 square divided by 0.1 minus 4.07 times 10 to the power of negative 3. And therefore, just calculations, approximately it's going to equal to 1.8 times 10 to the power of negative 4. So these are the two types of the problems. One type, they give you the concentration and the Ka, and you need to calculate pH. And the second type, they give you the pH and the concentration, and you need to calculate the Ka. Now, similarly, we were talking about the weak acids. Now we are talking about the weak bases. And if we have this example problem, for example, about the weak base, let's say the ammonia NH3, when it reacts with water, also it's a reversible reaction, and it will give you NH4 positive plus OH negative. We need to write the Kc for this reaction, which equals to products NH4 positive concentration multiplied by concentration of OH negative divided by the concentration of NH3 multiplied by the concentration of H2O. So the concentration of the product divided by the concentration of the reactants. But don't forget that the water here is liquid, so its concentration is constant. That means constant here multiplied by this constant is going to equal a new constant, and we call it the base ionization constant. And it's only for the weak base. So it equals to Kb now equals to the concentration of NH4 positive multiplied by the concentration of OH negative divided by the concentration of NH3. All of them should be at equilibrium. So all of them should be at equilibrium. Now, here are some Kb for some weak bases. Of course, in the exams, these tables are given to you, or at least the Kb and the Kc values will be given to you. Without being late, because I want to make this video short to finish this topic, because next topic is going to be for diprotic and triprotic acids. Let's solve this example. What is the pH of 0.4 molar ammonia solution? We're going to start with the ICE table after we write the ammonia solution, which is NH4OH yields to NH4 positive plus OH negative. We need the ICE table. That means here the initial it was 0.4, here it was 0, and here it was 0. At the change it's going to be negative x, here positive x, and here is also positive x. In the equilibrium, at the equilibrium is going to be 0.4 minus x, x, and x. Now the Kb for this for the ammonia is going to be x squared over 0.4 minus neglected x, and which equals to, when we go back to the ammonia, is going to be 1.8 times 10 to the power of negative 5, so equals to 1.8 times 10 to the power of negative 5. We solve it for x, that means x squared equals to This number, 1.8 times 10 to the power of negative 5, multiplied by 0.4, which equals to 7.2 times 10 to the power of negative 6. That means x, we need to take the square root, which equals to 2.68 times 10 to the power of negative 3 molar. This x represent the OH, not the H. So pOH, we need to take the negative log for the concentration of OH negative. Never do a mistake about this. So it equals to negative log this answer, which equals to 2.57. Therefore, the pH will equal to 14 minus 2.57 and equals to 11.4. The ionization constant of conjugate acid and base is very simple. The Ka, but here don't make a mistake. It's the pair. That means this is the acid and its conjugate base. This is now the acid, sorry, this is the base and its conjugate acid. So we have here Ka and we have Kb, and for the water we know that it's Kw. Always Kb multiplied by Ka equals to Kw, which equals to 1 times 10 to the power of negative 14 at 25 Celsius. The lesson for now has finished. I hope you guys learned something new today. If you have any questions regarding the electrolytes, weak acids, and weak bases, please write in the comments. I will read all the comments and I will reply to you as soon as possible. Have a nice day. Bye-bye.